Dear students, I am Khandakar Fazda Rabbi, lecturer, Milestone College, Uttara. Today, I discuss with you some important mathematical problem from chemistry first paper, chapter 4. Dear students, we discuss about some mathematical problem from pH now, and we use this formula to solve our mathematical problem. Our first formula is pH equal to minus log of molar concentration of hydrogen ion, POH equal to minus log of molar concentration of hydroxyl ion. And our next formula, pH plus POH equal to 14, and alpha equal to root over Ka by C. Alpha is degree of dissociation. We use this formula, this 4 formula, for weak acid and base. For weak acid, we use alpha equal to root over Ka by C, and for weak base, we use alpha equal to root over Kb by C. And for weak acid, molar concentration of hydrogen ion equal to alpha C. C is the given value of concentration of weak acid. And concentration of hydroxyl ion, molar concentration of hydroxyl ion equal to alpha C. We use for weak base this formula. And for acidic buffer solution, we use pH equal to pKa plus log of concentration of salt divided by concentration of acid. And our next formula is for basic buffer solution, that is pH equal to 14 minus pKb minus log of concentration of salt divided by concentration of base. Now, our first mathematical problem, calculate, first one, calculate pH of 0.1 molar HCl. Here, the molar concentration of HCl is 0.1. So this is the molar concentration of hydrogen ion. That means given molar concentration of hydrogen ion equal to 0.1 molar, we get pH equal to minus a log of molar concentration of hydrogen ion. Here given the molar concentration of hydrogen ion is 0.1 molar. So we use this value minus log of 0.1, and we get the pH value is 1. Our next mathematical problem, calculate pH of 0.05 molar H2SO4. Here, one thing we have to know that here in sulfuric acid, 1 mole sulfuric acid, from 1 mole sulfuric acid we get 2 mole hydrogen ion. So the concentration of hydrogen ion equal to 0.05 into 2, because we get 2 mole hydrogen ion from 1 mole sulfuric acid. And we use the formula pH equal to minus log of molar concentration of hydrogen ion, and that is minus log of that is 0.05 into 2, and we get value 1. So the pH of 0.05 molar 0.05 molar sulfuric acid is 1. And our next mathematical problem is calculate the pH of 2.5%. Calculate pH of 2.5% sodium hydroxide solution. Here given the percentage of sodium hydroxide solution is 2.5%. So at first we have to calculate the concentration, molar concentration of this sodium hydroxide solution, and we use the formula S equal to W into 1000 divided by mv. Here W equal to 2.5 gram and volume V equal to 100 ml, and molecular mass of sodium hydroxide, that is 40, and molar concentration S equal to what? Now S equal to W 2.5 into 1000 divided by 40 into 100, and we get the value 0.625 molar. So the molar concentration of 2.5% sodium hydroxide solution is 0.625 molar. Now one thing, here given sodium hydroxide solution, so at first we had to calculate the pOH of this solution, and then we calculate the pH of this solution. So we get pOH equal to minus log of molar concentration of hydroxyl ion. Here we get the concentration of hydroxyl ion equal to 0.625, so we write the value here 0.625, and we get the value 0.20. So the pOH value of sodium hydroxide solution is 0.20. Again we get pH plus pOH equal to 14. So pH equal to 14 minus pOH, that is 14 minus 0.20, and the pH value of this solution is 13.80. Okay, now we calculate the pH of 0.1 molar acetic acid solution. Here calculate pH of 0.1 molar CH3COOH solution, and given Ka value equal to 1.8 into 10 to the power minus 5. Here we see that here given the acid is acetic acid. This acetic acid is an weak acid, so we cannot calculate the pH of this acid directly. At first we have to calculate the degree of dissociation of this acid, then we calculate the concentration of hydrogen ion, and after that we calculate the pH of this solution. Now we get for acidic buffer solution alpha equal to root over Ka by C. Here given the Ka value equal to 1.8 into 10 to the power minus 5, and given concentration is 0.1 molar. So 1.8 into 10 to the power minus 5 divided by 0.1, and we get 0.0134. Again we get molar concentration of hydrogen ion for weak acid, that is alpha C, and value of alpha equal to 0.0134 into concentration of given solution is 0.1 molar, that means 0.1, and we get 1.34 into 10 to the power minus 3 molar. Now we calculate the pH again. Now we get pH equal to minus log of molar concentration of hydrogen ion, and we get the molar concentration of hydrogen ion of this weak acid is 1.34 into 10 to the power minus 3 log of 1.34 into 10 to the power minus 3, and we get the value 2.87. So the pH of 0.1 molar acetic acid solution is 2.87. 2.87. Now we calculate the pH of 0.01 molar ammonium hydroxide NH4OH, and here the given value of Kb equal to 1.8 into 10 to the power minus 5. This ammonium hydroxide is a weak base, and that's why we at first we have to calculate the degree of dissociation alpha, then calculate the molar concentration of hydroxyl ion, and then calculate POH, and after that we calculate the pH of that solution. So at first we get alpha equal to root over Kb by C, and this is 1.8 into 10 to the power minus 5 divided by given concentration 0.01, and we get the value of 4.2426 into 10 to the power minus 2. Now concentration of hydroxyl ion equal to alpha C. So we write here 4.2426 into 10 to the power minus 2 into concentration of given ammonium hydroxide solution is 0.01 molar. So we multiply here 0.01, and we get 4.2426 into 10 to the power minus 4 molar. Again POH, we get the concentration of hydroxyl ion solution, so we have to calculate the POH minus log of concentration of hydroxyl ion minus log of 4.2426 into 10 to the power minus 4, and we get the value 3.3723. This is the POH value of this ammonium hydroxide solution, and again we get pH plus POH equal to 14. So pH equal to 14 minus POH, that is 14 minus 3.3723, and we get the value 10.6277. 10.6277. So the pH of 0.1 molar ammonium hydroxide solution is 10.6277. Dear students, here given our mathematical problem, given 30 ml 0.15 molar acetic acid and 40 ml 0.025 molar sodium acetate. the Ka value of this acid is 1.8 into 10 to the power minus 5. And our question is calculate the pH of the mixture of A and B. That means if we mixed up this acetic acid and sodium acetate solution, then we have to calculate the pH of this mixture. And we can say that this mixture is a buffer solution because here acetic acid is an weak acid and this sodium acetate is its salt. That means sodium acetate is the salt of this acetic acid, and that's why this is a buffer solution. That means acetic acid CH3 COOH plus CH3 COONA. This is a buffer solution. This is a buffer solution. So in the mixture, concentration of acetic acid CH3COOH, that is CH3COOH, third bracket, that is the concentration of acetic acid is 0.15 into volume of acetic acid, that is 30 ml, divided by total volume. Total volume of this mixture is 30 plus 40, and we get the value is 0.0642 molar. And in mixture concentration of sodium acetate CH3COONA, that means CH3COONA, that bracket, is the concentration of sodium acetate, that is 0.25 into volume of sodium acetate, that is 40, divided by total volume of the mixture, that is 30 plus 40. And here we get the value is 0.1428 molar. 0.1428 molar. Now we know that for acidic buffer solution, pH equal to, we get for acidic buffer solution pH equal to pKa plus log of concentration of salt divided by concentration of acid, and we get pKa equal to minus log of Ka plus log of salt is CH3COONA divided by CH3COOH acid, and the value of Ka minus log of 1.8 into 10 to the power minus 5 plus log of concentration of sodium acetate, that is 0.1428 divided by concentration of acetic acid, that is 0.0642, and if we calculate the value, then we get 5.091. So the pH of the mixture is 5.091. Our next mathematical problem, here given 30 ml 0.1 molar acetic acid and 20 ml 0.1 molar sodium hydroxide, The Ka value is 1.8 into 10 to the power minus 5. Our question is calculate pH of the mixture of A and B. Here we see that CH3COOH is an weak acid and NaOH is a strong base. So the reaction is like this: CH3COOH plus NaOH reacts and it produces CH3COONA plus H2O. Here it produces salt of acetic acid, and at initial stage here given acetic acid solution is 30 ml and sodium hydroxide solution is 20 ml. Their concentration is equal. So after reaction, here 20 ml sodium hydroxide, this 20 ml sodium hydroxide reacts with 20 ml acetic acid. That means 30 minus 20, and this 20 ml minus 20, and we get 20 ml sodium acetate solution. So after reaction we get 10 ml 0.1 molar acetic acid, and we get after reaction 20 ml 0.1 molar sodium acetate. Now in the mixture, concentration of acid, here we see that after reaction we get only acid and its salt. So this one is an acidic buffer solution. So in this acidic buffer solution mixture, or in this mixture, the concentration of acetic acid CH3COOH, concentration of acetic acid is concentration of acetic acid 0.1 into volume of acetic acid 10 divided by total volume here 30 plus 20, so 30 plus 20, and we get the value is 0.02 molar. And in the mixture, concentration of sodium acetate CH3COONA, we get the concentration of sodium acetate, that is 0.1 molar, and volume of sodium acetate, that is 20 ml, 20 divided by total volume 30 plus 20, and here we get the value 0.04 molar. Now pH of the mixture, we get for acidic buffer solution pH equal to pKa plus log of concentration of salt divided by concentration of acid, or pH equal to minus log of Ka plus log of salt CH3COONA CH3COOH, and minus log of 1.8 into 10 to the power minus 5 plus log of concentration of sodium acetate is 0.04 divided by concentration of acid, that is 0.02 pH, or pH equal to 5.05. So the pH of the mixture is 5.05. Dear students, our next mathematical problem, here given 150 ml 0.2 molar acetic acid and 160 ml 0.1 molar sodium hydroxide. Our question is, calculate the pH of the mixture of A and B. Here we see that the concentration of acetic acid and concentration of sodium hydroxide is different. So at first we calculate the mole number of this acetic acid and sodium hydroxide. So mole number of acetic acid is 150 into 0.2, and here the unit of volume is ml, but to calculate a mole number we need unit of volume is liter. So we divide 150 into 0.2 divided by 1000 mole. Now mole number of sodium hydroxide, that is 160 into 0.1 divided by 1000. We use 1000 to convert this unit into liter, mole, and here we get the value 0.03 mole, and for this we get 0.016 mole. Now if you see the reaction, CH3 COOH plus NaOH, it produces CH3 COO Na plus H2O. At initial stage we get here 0.03 mole, 0.016 mole. After reaction we get here 0.03 minus 0.016, 0.016 minus 0.016, and here we get 0.016 mole. At initial stage mole number of sodium acetate is 0 and water equal to 0. I can repeat. Initial stage sodium acetic acid 0.3 mole, sodium hydroxide 0.016 mole, and sodium acetate equal to 0, acetic water 0. But after reaction 0.016 mole sodium hydroxide reacts with 0.016 mole acetic acid, and it produces 0.016 mole sodium acetate. So here we get 0.014 mole acetic acid after reaction, and 0.016 mole sodium acetate. So here we write pH of this mixture, because here after reaction we get acid and its salt. So this one is acidic buffer solution, and for acidic buffer solution we get pH equal to pKa plus log of salt by acid, their concentration, and we get minus log of Ka plus log of salt here, CH3COO Na and CH3COOH. Here we use mole number, so we use mole number minus log of 1.8 into 10 to the power minus 5 plus log of mole number of sodium acetate 0.016 divided by mole number of acetic acid 0.014, and the pH of this solution mixture is 4.8. Here we use mole number instead of concentration, because if we use mole number then or if we calculate the mole number, then we can use mole number instead of concentration, and the pH of the mixture is 4.8. Dear students, here our next math. The heat of combustion of carbon disulphide, sulfur and carbon are respectively minus 1109.17, minus 297.39 and minus 394.55 kilojoule per mole. Find out heat of formation of carbon disulphide. At first, here the reactions are carbon disulphide reaction 1 reacts with oxygen and it produces carbon dioxide plus sulfur dioxide. Here one carbon present, so 1 mole carbon dioxide produced, and number of sulfur equal to 2, so here we multiply 2 sulfur dioxide produced, and to balance the oxygen here 2 into 2 4 oxygen, and here 2 6 oxygen, so we have to multiply here 3, and the heat of combustion of sulfur dioxide, that is del HC CS2 equal to minus 1109.17 kilojoule per mole. And our second reaction, sulfur reacts with oxygen and it produces sulfur dioxide as solid gas. This one is also solid. Here we use gas, and in this term here given the combustion enthalpy of sulfur is 297.39. we know that the combustion enthalpy of sulfur is equal to the formation enthalpy of sulfur dioxide. So we write here del HF SO2 equal to minus 297.39 kilojoule per mole. And again, reaction 3, combustion enthalpy of carbon, that means C, reacts with oxygen and it produces carbon dioxide gas, solid gas. Again, the combustion enthalpy of carbon equal to the formation enthalpy of carbon dioxide. So we write here del HF CO2 equal to minus 394.55 kilojoule per mole. So according to our first reaction, we know that the heat of reaction, del H equal to total heat of formation of products minus total heat of formation of products minus total heat of formation of reactants. So according to our first reaction, we can write here del HC, combustion enthalpy of sulfur carbon disulphide, equal to formation enthalpy of del HF CO2 plus 2 del HF SO2. This is total formation enthalpy of product minus del HF CS2 plus 3 del HF O2. That means combustion enthalpy of carbon disulphide equal to formation enthalpy of carbon dioxide plus formation enthalpy of sulfur dioxide minus formation enthalpy of carbon disulphide and formation enthalpy of oxygen. So we have to calculate here del HC, formation enthalpy of carbon disulphide, that means del HF CS2 equal to del HF CO2 plus 2 del HF SO2 minus 3 del HF O2 and here minus del HC CS2 or del HF CS2 equal to formation enthalpy of carbon dioxide equal to formation enthalpy of carbon dioxide equal to minus 394.55 plus 2 into minus 297.39 into minus 3 into 0, because formation enthalpy of oxygen equal to 0, minus combustion enthalpy of carbon disulphide, that is minus 1109.17, and here we get the result is minus 119.84 kilojoule per mole. So the formation enthalpy of carbon disulphide is minus 119.84 kilojoule per mole. Students, this is your SW. Both methane and ethane can be used as fuel. The standard heat of formation of methane, ethane, carbon dioxide and water are minus 74.89, minus 84.52, minus 393.30 and minus 220.90 kilojoule per mole respectively. Find out which one is preferable in use as a fuel between the two.